In this video, I'll be continuing to discuss organic nitrogen compounds. So in the previous video, I think I said topic 18, but this should be topic 19 of Edexcel Chemistry IAL. So excuse me, but that's topic 19, okay? It's topic 19, and I'm going to discuss the part 2, amides and polymers, okay? So let's start. So first of all, we can make a primary amide, which basically means that on the nitrogen it only has one alkyl chain attached to it. So with an acyl chloride and an amine or ammonia basically. So we have the ethanol chloride over here, acyl chloride, and we have the ammonia over here. They can react to form an ethane amide. So you'll see that this is a condensation reaction because we are removing one H from the ammonia and the chlorine from the ethanol chloride. And so, yeah, HCl is being removed and we get the amide bond over here, C double bond O, NH. And the next example, we have the ethanol chloride reacting with a primary amine. Okay, so it could be an amine, not just ammonia. So when they react, they're going to get it's the same condensation reaction. We're going to remove one H and one Cl. So you're going to get the secondary amide. In this case, it's going to be N-methyl ethane amide because the nitrogen containing group was the methyl, right? Methyl amine. And so ethanol chloride, so ethane amide. Okay, so that is our making amides. So yeah, again, condensation reaction. We're going to look at the polymers now that we know condensation reactions. So condensation polymers, we have nylon first of all. So first of all, one of the reactants that we need to make nylon is a hexandioic acid. Okay, so we have 1, 2, 3, 4, 5, 6 carbons, and on each edge we have the carboxylic acid groups, right? So we can actually shorten this chain because it's basically repeating CH2 not branches, but alkyl chain. So it's going to be our hexandioic. This you can shorten it like this, and this is going to be our first reactant. Okay, and we're going to also react it with 1,6-diaminohexane. So this is basically the same structure. We have 6 carbons, just a straight chain of 6 carbons, and we have amine groups on each side instead of the carboxyl groups. Okay. And condensation reactions will occur. And the OH over here from the carboxyl group and the H on the amine group is going to be removed, forming water. And so we're going to get an amide bond over here like this. This is our amide bond that has formed, okay? So you can make more amides over here on either side of the molecule. Obviously, on this side is going to be our more amines, and over here it's going to be the hexandioic acid, right? So yeah, one thing you need to notice is when you're doing condensation polymerization, you need per one molecule 2 functional groups, okay? Whether if it's carboxyl group, or amine group, or amine and a carboxyl group, okay? So we need 2 functional groups. So the repeat unit of nylon 6. So 6 basically just stands for how many carbon chains were there in the 2 monomers that we used, okay? So that would be this. This is the shortest repeating unit. So the N over here was bonded to C double bond O, right? But that would be the same as this C double bond O, so you don't have to, you should not include it in the repeating unit, okay? So that is the shortest repeating unit that you should draw from this structure, okay? I mean, that is already a repeating unit, isn't it? Anyways, another condensation polymer is proteins. In this case, this is not acid and acid and then amine and amine in the 2 different monomers. This time we're going to use something called an amino acid. Okay, so there is an amine group over here and the acid group over here, so that's why they're called amino acids. And This is the general structure of all amino acids. Basically, the carbon, central carbon over here, is bonded to H, first of all, and a carboxyl group, carboxylic acid group, and we have the amine group, and then we have the variable group. We have 20 variations of this group because we have 20 amino acids that we can find in, Earth right now. So basically, same condensation reaction occurs with different amino acids. So we have the carboxylic acid group and the amine group reacting, water is being removed, and we can just continue this on and on and on. Continuing to join amino acids, and that's how you make proteins. Okay, proteins are an example of polyamides. Okay, so yeah, we get all the amide bonds, and they can continue. Okay, so this is just like three amino acids joined. Yeah. If the R groups are different, you cannot write the repeat units, obviously, right? If the R groups are the same, which doesn't really occur in nature, probably not the repeating units of, no, I don't think there are many proteins that have same amino acids, just, yeah, anyways. If the R groups are different, you cannot write the repeat unit, right? And we're now going to look at some addition polymers. So this requires monomers to have carbon-carbon double bonds. Okay, yeah, that is the most important factor, carbon-carbon double bonds. If they don't have carbon-carbon double bonds, we cannot make addition polymers. Okay, so in this case, it's addition because we don't waste any, we don't produce any other molecules. Okay, in condensation reactions, we had HCl or H2O removed, right? So first of all, we're going to look at the polypropene amide. So we have the propene. First of all, we have 1, 2, 3 carbons, 1 double bond, and we have the amide over here, amide group over here. So we cannot put the amide group over here because it already has a double bond and we don't have enough bonds, right? So obviously it should be like that. And I'm going to kind of redraw this structure so that it's easier for us to make a polymer. Okay, so you can write it like that. So my amide has been reduced to just CONH, like that, right? So if you write the balanced equation, basically, we first of all need n number of the monomers we have, and then we're going to have the continuing chain of this addition polymer. So what happened is basically, you can think of it like this. Amongst the two bonds, you just break one of them, and half of them have been extended to the either side, and you have many of those monomers that have broken one of the double bonds, and then have half bonds on the either sides, and the half bonds meet and it forms a full bond. Yeah, so that is how I like to think about as for addition polymers. And yeah, if you write the balanced equation, you would have n number of this monomer, and then you would have the n repeating polymer. Okay, so that is how you need the square brackets if you're writing the balanced equation. Okay, and don't forget your n's at the right positions. Okay, so many people write this n on the left, like over here, but that is kind of incorrect, so be careful. And if they tell you to write the repeat unit only, not the balanced equation, you can just write this. You don't need these square brackets. Okay, all right. And as you can see, because the amide group, they can form hydrogen bonds with water, the polymer can absorb water, okay, and become softer when it has water attached to it. So therefore, it is used in soft contact lenses, okay? So yeah, contact lenses have to be soft for it to go into your eye, right? Which is wet, mostly. And we have the second addition polymer that we should look at, which is a polyethanol. This is an ethene with an alcohol group on it. Very easy, a lot more simple, and not a lot more, but a little more simple than polypropene amide. So same thing, the balance equation would look like that, both n on the left side on this side and the n on the right bottom of these square brackets. And when you have to write the repute unit, it will be like that. So don't panic when sometimes they give you something that looks like this, you know. It's the same thing, you just have to move that OH bond to the bottom, right? It's the same thing. Don't get scared. And yeah, these also can form hydrogen bonding, right? Due to the ability to form hydrogen bonds, this is water soluble. So now this one is not only just water absorbing, it's soluble. Okay, so therefore it's used in dissolving laundry bags, especially in hospitals because we don't want any contaminations, and dissolving detergent capsules, like liquid tabs. So those like little liquid detergent capsules that you throw it in the washing machine together, and then it dissolves, and then it releases the liquid detergent, and so now we're going to look at the amino acid behaviors. So this is our amino acid, just like I mentioned, carboxylic acid over here, amine group over here. If you add a base, it's going to react with the acid group, obviously, right? The OH minus ion, hydroxide ion, is going to donate the lone pair from the oxygen and accept this H plus and give an ion structure like that. And we have the water molecule being removed. And if you add an acid, an opposite from, we add the base, and this time we're going to add the acid, it's going to react with the basic group, which is the amine group. Okay, that is going to basically donate its lone pair to the hydrogen ion, which is the proton, and form this ionic structure again, NH3 plus. And yeah, so this, which means that amino acids can exist in certain pHs as zwitter ions. So what that is that equal numbers of positive and negative charged functional groups are present in the same molecule, okay? So that is one behavior that you should know about amino acids. And also, aqueous solutions of amino acids can polarize plain polarized monochromatic light. Okay, so what that means is that they can show optical isomerism. That is because they have a chiral carbon with 4 different groups of atoms attached to it. So you can see that this carbon over here is the chiral carbon, right? Because H is a different group, NH2 is a different group, R is going to be a different group, and we have the carboxylic acid. So one exception is glycine. I don't think you should know basically, the name of the amino acid, but, in glycine, an amino acid, this has H as the variable group, meaning that it's going to be the same as this H, right? So this carbon is not going to be a chiral carbon. So it's not going to show optical isomerism, okay? So that's one exception that you must, bear in mind. So yeah. And also the aqueous solutions can, it says it can polarize plain polarized monochromatic light, but that is when we don't have a racemic mixture. So a racemic mixture means that we have 2 equimolar amounts of the enantiomers, and enantiomers is the 2 different optical isomers. So optical isomers is when you have 2 mirror images that cannot be superimposed to each other, okay? So it means that we have the same amount of this and this, so it doesn't really polarize the plain polarized monochromatic light, okay? So I'll explain more about optical isomerism in a different video, but if you hopefully, have a read about it from other textbooks or, websites, that would be easier to understand what I'm saying over here. But anyways, that is it for this video, and I'll see you in a different topic, hopefully very soon. So, bye.